Hello and welcome back to the second lecture on generalized linear models. I've just simply copied from images online a bunch of textbook covers about generalized linear models. There's also, you notice, a few titles that include mixed models, which we'll get into in a couple of weeks. The two on the right that I've left larger are a couple I have on my shelves and I keep referring back to. They're specifically associated with ecology in terms of the data sets that they work with in the examples. But notice that there's a proliferation of generalized linear models, advice, and references to be able to learn how to do this. The ones I have used, like I said, are the two on the right, but also there's a large book about how to do R in general that includes some handy chapters on GLMs that's written by Crawley. So you should get the sense from this then that this has been this explosion in terms of the access of GLMs to people for using in their analyses, but also references on how to learn how to do them. So maybe this will be one more introduction that might be of use to you. So I want to just simply stick with one data set to play around with GLMs and compare that to the classic approach of using an LM. So I'm going to just work with this one example, and it comes with the mass package, which is loaded by default in R. It's a very convenient set of tools for a variety of different kinds of analyses associated with a book that was written a while ago. You can read more about it in the documentation on the mass package. Inside that package, there's a data set on cars from 1993, and so that data set is simply called Cars 93. So if we load the mass package and get the data, we can say library mass data cars 93, and then just simply I'm going to attach that because that means that I don't have to keep referring exactly back to that same data set over and over again. So inside of that data set there are lots of variables, and I'm going to choose the MPG in the city, miles per gallon in the city, as a response variable over and over again, and I'm just going to begin with a simple regression of bivariate model where I'm going to use weight to predict the MPG in the city for cars. Okay, and I'm going to use linear models and GLMs both. So what I'm going to do first is just squint at the data, and so if I take a histogram of MPG in the city among a bunch of different cars, you can see a whole lot of cars in 93 had quite low MPG, and then only a very few were pushing up into what we might think of as the hybrid and electric car. Well, electric cars surpass that now. The hybrid range is up in here. So most of the cars were achieving quite low MPG in 1993. In fact, it hasn't skewed that much better recently because we have so many big SUVs in the road. Okay, so how would I deal with this in the classic approach? Well, I would hope to transform it to make the data look more normal and then be able to explain that trend by weight, right? So the classic approach would include some transformations, and I might try a square root transformation where I might call it SQ-MPG, and maybe a log transformation. I'll just use log 10 here. You could use ln as well if you wanted to. And so the LG-MPG is my model that would be just a transform. And then if I do histograms of those two, the square root makes it look a little more normalish, but it looks like it's still a bit skewed out to the right with a big tail out here. The LG is a little bit better, and it's still a little bit off-center, but I might have said, well, that's going to have to be close enough, and I would try perhaps using a log transform data. So in that classic approach, I would then take an LM, a linear model, where I'm relating the log transform data to weight, right? And I would get this output, looks like this. So it shows my residuals centered around this value, this median, and the quartile out and the quartile, down and up look pretty balanced. The numbers are about the same distance away from here, and the minimum and the maximum values look also like it's not too bad. The estimates are simply the coefficients. So I have this linear model of my LG MPG, the log of miles per gallon in the city, is this intercept value minus this effect due to weight, right? So it's a negative value. So you can see that the more weight there is, the more per pound of weight, the more I reduce the MPGs. Okay, it's not a bad model in terms of the R squared that we get, and the residual standard error looks pretty small. It's obviously significant because we have strong coefficient here. So the AIC, which I asked for separately on that model, is also looking like it's potentially pretty low. It's a negative value. Well, I can repeat that classic approach just using an LM, but I can do that inside of GLM. So here I'm going to repeat this now inside GLM, and I simply said GLM, the same equation here, and then the formula was just simply specifying a family of Gaussian, okay? So this is saying the exact same thing, and just to convince you, I'm going to look at the coefficients. Let's just remember these 1.78 and minus 1.46 to 10 to the minus fourth, okay? Let me go back to what I had before, 1.78 and minus 1.46 to the negative fourth, right? Let's look at the r squared again. In the classic models of 0.7803, and in GLM, I actually don't get an r squared. Notice that. It doesn't produce that kind of output. It's responding based on deviance instead. So, but hopefully you can see that I'm getting the same basic model being conducted both approaches, okay? Same estimates, same significance values. I don't see an r squared value here. That's one of the things that's convenient about LM and that we're accustomed to, that you do not get in a GLM. But I can look at the classic model also by the residuals. And so if I look at the residuals of that classic approach, it looks like there's some sort of curvature. It looks like maybe some sort of spreading out of the homogeneity of variance being potentially a problem. It looks a little tighter over here on this side, looks a little wider here in the middle. There's clearly a couple of oddballs that are sticking up high and one down low, and we can see those as causing some sort of problems for the normality curve as well, right? So the classic approach looks like we're getting not too bad. It's not wildly skewed on one end versus the other in terms of the shape of this residuals pattern. But on the other hand, I've got some sort of problem with homogeneity of variance that I wish I could reduce a little bit better, okay? So I could start thinking about the different approaches, the different families that I have available to me in the GLMs. So I can think about that table I showed at the end of the last lecture, and I could see that the Gaussian model would be a simple way to go, and I did that inside GLM on the log transform data. But I could also start thinking about other ways to evaluate the distributions in a log kind of approach, like looking at log transform data. I could use a link that is a log in a Poisson. I can do the same thing inside the gamma. I could say a log link inside gamma, and in the inverse Gaussian as well. Now there's some of the other factors I have to take into account over here on which kind of family to be choosing. The idea with a Poisson is that it's count data because I'm supposed to be using integer type data in there. The gamma is freed up from that. I can deal with real numbers, in other words decimal numbers, again greater than zeros. And I could use a log link inside gamma to try to represent what I thought was the best log transform earlier. So I'm going to play around with a couple of those different options. I'm not going to go into the more advanced versions down here, and binomial would not be appropriate here because we're not playing with binary responses. So if I try this GLM approach, I'm going to try a gamma family because I can deal with the real numbers that are greater than 0, and I can choose an identity link that would be a gamma, just simply trying a gamma distribution that would be related to the original Gaussian distributions. And then I can also play around with a log transformation by using a log link inside the GLM as well. Okay. So here's what I tried. I used the GLM. I specify the same formula. Notice that these are not log transformed. This is putting in the original values. And I say that family is a gamma, but now I say link is identity. All right. So this is not transforming in any way other than trying to customize the fit of the data using a gamma distribution. It's allowing gamma to just try to work on the raw values. And so I get the same sort of output coming out. It looks like the quartiles are a little bit different, upper and lower. That is indicating some sort of skew here. But I wouldn't be entirely surprised by that because I'm not transforming anything. I'm sticking to the original values. Here's my intercept and the coefficient again for the slope. Notice, of course, they're significant, but I have lots of data. That's not a surprise. And then what I'm getting again are these null deviances, and I automatically get an AIC value. So I'm going to focus in on the AICs as a way to compare among models. So here my AIC is a 439. Let's remember that. Now let's just look at how that might differ if I used a log transformation inside the GLM. I should say that better. I'm going to use a log link inside the gamma function. So now the only thing I've changed, notice that this stayed the same up here. All these things, variables, etc. are the same, except now this is log. Let me go back. The previous screen I showed you, this was identity. Now what I'm doing is simply calling this log. And that jumping, of course, meant that the values are changing a bit. And now I have a different AIC. This is a 424 when I use a log link. Okay, let me go back to the previous screen. And that identity one was a 439. Well, that actually is a pretty substantial difference in AIC. So let me just summarize. If I look at the GLM of the log values, I get a great AIC. It's a minus value, right? If I look at the GLM of the identity raw values, not log, I get a much higher AIC. And if I play around with a log link inside gamma, I make a slightly better AIC. But wait a minute, this is cheating. If you might remember, you can't use a log transformed response to compare to log transformed responses. This log transform will of course be on different units and of course has an entirely different computation and would have a much lower AIC only because it was log transformed. These MPGs are in the original units and those are fair comparisons, the second two. The first one is not a fair comparison. So we can't really put that one in there. We have to think about just these two in the GLMs where we're dealing with the original original log units being out of the picture. Now we're playing with original MPGs. Okay, so the only difference here really is I'm evaluating a non-log transformed but using gamma distribution and a log transform kind of linkage inside using gamma distribution. And the AIC is substantially better. If I look at the AICC table that you can do in the BBMLE package, you can see that it is much more likely to be the most plausible model between the two. And that's just the two AICs I showed you already. Okay, so another possibility, if I go back to the table we had here, remember I was just focusing on gamma just now, another possibility to play around with log linkages would be in the Poisson distribution. Although it's intended for integer data like counts, we could try and see what happens if we were to have run that Poisson. So what would have happened if we used the Poisson? That's what I do right here. A GLM, we're using the same formula, but now all I do is change the family to represent the Poisson model with the link being the log, quote, transformation, unquote. Again, we get these values that look like there might be some skewiness, but not too bad. And we get coefficients once again. And let's zero in on the AIC once more. It's a 488, whereas what we were seeing before were substantially better. Okay, so the two gammas, one where it was a log link, I should say link is a link was the log function. This one was the identity function. Now Poisson of a log actually turns out to be worse in AICs than the original identity function. So using a Poisson didn't work well, even though you might have thought it could because it's supposed to be based on log data. Just to remind you, here's that table again. You could use log inside this link, but the Poisson distribution worked substantially less effectively than the gamma distribution based on a log. So our AIC table then, among the three choices, comes back to using my gamma distribution with the log link. Okay, so let me look at the residuals for that one, and it looks rather like what we saw before when we did the log transformation on the data in the classic approach. We have that curvature that's still in there. It looks like we have a couple of the oddballs are still out there. The oddballs are still pulling the data a little bit, but this is actually very similar to what we had with the original classic approach of an LM on log transform data. Let me just go find that residual again in just a moment. And the classic approach looked like this. Very similar to what we have now with the gamma model log link. I'll flip to that in just a moment. Ready? So we're looking at that one for the classic one and this one for the log link. I know the axes are stretched slightly wider, but it's basically the same scatter. It's the same basic pattern. So what have we done? We've just simply bypassed this classic approach. Instead of transforming the data to fit the model assumptions, what we've done is we've matched model assumptions to fit the data. It's a little more simple in that we're not hunting around through a bunch of different transformations and hoping that one works. We have actually a number of options to choose among those model assumptions as well. We have to interpret the classic data in the transform scale. If you're dealing with log data that are log transformed and then run in a classic LM, it's best to interpret those things in the log scale. You need to back transform to try to make those conversations in the original units, and that can be awkward. You have to be really careful with back transforming. We can retain the original scales in the GLMs that used a log linkage, for example, in the gamma distribution. We can match those classic data to simple models then. So we're actually using, you can use a classic LM inside GLM. So in other words, the GLM allows you to work with the old school as well as the new school of, for example, gamma distributions. The classic models can get really awkward if you have multiple responses and complex data, because you're talking about log transforming one variable and square root transforming another variable. If you want to compare among those different responses, it can be awkward. Square root of one response and log transform of a different response, it's hard to evaluate all these different things. If you get around to just working on GLMs, everything stays in those original units, and so it can be more elegant for these complex kinds of comparisons. All right, so hopefully you can see that the GLM matches perfectly with the original LM, or you can just use a a link identity in a Gaussian distribution, and you get the exact same thing you would have in an LM. But you have these other approaches. I think fundamentally it can be handy in that you're matching model assumptions to fit the data rather than what we kept doing over and over again, which was changing the data to try to fit the more simple, rigid, if you will, model assumptions of linear models. So let's try to play around with this with a more complex model. I'm going to stick to the same response, but we'll try a bunch of different predictors. And I'm not going to worry so much whether some of these things are autocorrelated as they would be. A VIF kind of approach might delete some of these variables. But let's just see what happens if we get something more complicated. I can just play around with cars 93 again. I'm still sticking with MPG.city as my response, but now I'm going to say that weight and horsepower and revolutions per minute and the number of passengers and the manufacturer and the origin might all be predictors of this, ignoring VIF, etc., like I said. So let's see. I could use the classic GLM kind of model where I say it's a Gaussian family, which means that my Gaussian original LM is what's running right here in my second Gaussian version of a GLM. That's why I'm numbering it 2, because I did one before. I have another gamma where I'm going to look at this log kind of linkage where I expected that to work because it somewhat did pretty well as the LM did in the past when I had log transformed LMs. So I'm going to use this as my log transformation, and I'm going to try the Poisson as well, and I'm also going to try the log linkage is there and see how those work. Okay, so let's just look at the residuals, and rather than dealing with the models. Here's the Gaussian one. We can see we got a fair amount of bend in this. We also have those oddball points out there. This is having some problems with normality. There's definitely some curvature away from the line, and this is indicating some pretty strong problems if we had just left with it as original Gaussian distribution, no transformations at all. If we use this log linkage, which is sort of like a log transformation, it's better. It's almost like what we saw before. We just added on a couple of extra variables, and I made this more of a square box rather than a rectangle, so it makes this curvature a little bit more apparent. The variation is pretty even up and down with a couple of oddballs, and the fit is better to the normality line in the QQ plot. Let me jump ahead to one more, and I'm going to set aside this one. The Gaussian is not necessarily being good, so let's leave that one alone, and let's look at just the gamma and look at the Poisson. So now the gamma's on the left. I just repeat that same pattern, so I can compare it over here to the Poisson, which is also using a log. And now I say, well, man, they look kind of the same. They look pretty similar to me. It's hard for me to eyeball left and right here and see some really strong differences. There's maybe a little closer pattern here for the log linkage in gamma than there is in the Poisson. It might be that the gamma is a little closer to the line, but it's hard for me to see a whole lot of residual pattern that's much different in the Poisson versus the gamma. So I'm trying to squint at these in the residuals, but you know what? Maybe I shall let AIC help me here too. AIC, remember, is going to evaluate these residuals relative to the model complexity and tell me which one's most parsimonious. So if I say AICC among those choices, and I left the Gaussian in there. Guess what? The Poisson has a higher AIC than the Gaussian model, and so the gamma comes out ahead once more, clearly far more plausible as a model. But interestingly, the Poisson is less plausible than the Gaussian, which I would not have guessed. So the AICs are also a really helpful tool here to help me evaluate the residual patterns. That's really what it's doing computationally, whereas I'm relying on my eyeball here with these plots. I kind of like the idea that the AIC can help me discern the residual patterns. So hopefully you see that GLM gives you some options to suit the model assumptions to the data. That was different from the classic approach where we transform data to try to fit this very one prescribed set of model assumptions, the normal distribution, the homogeneous variance that we get with the LMs. Okay, there are multiple options to work with. For example, notice I was playing around with different kinds of linkages inside gamma. You have different kinds of linkages inside Poisson, inside inverse Gaussian, etc., etc. That gives you more choices to play with. It also means you have more fussing around to choose among the different options. I would say that's a nice thing, but you also have to be more cautious about what you're doing. That's one of the advantages that R gives us. You have lots of rope to work with, but you also have to be careful about making your choices. Now, that means that you should evaluate these model choices using the residuals, and I think AIC is a nice guide, as I tried to illustrate when visually I have a hard time discerning the differences with residuals. So hopefully that gives you some introduction into how to see GLMs. Notice that we do the exact same thing we've been doing all along in an LM inside of GLM. So we don't lose anything with GLM. In fact, it's adding a bunch of other options to suit model assumptions to the data. Okay, we're going to continue to mess with GLMs the rest of the semester, and in fact, that will be a platform on which we can go forward with mixed effect models. And one more part of GLMs that we'll get to is going to be the logit functions. Let me just jump back to this. We play around with binomial data, and we're doing a logistic regression too. So really, GLMs are the platform for the rest of our course. All right, that's about it for now, and I'll talk to you next time.